Ladies and gentlemen, welcome to the elementary education of scientific Python, aka scipy, right? This is Christian Paul speaking once again, the socially awkward nerd at your service, and we are actually going to dig into another Python packaging called scipy, where they basically talk about fundamental algorithms, a bunch of stuff that, for folks that actually did physics, chemistry, engineering, biology, right? Any of the STEM fields where you'd be doing a lot of calculating and computing. Calc 1, Calc 2, Calc 3, bunch of matrix problems, partial differential equations, ordinary differential equations, PDEs and ODEs respectively for short. This is the package for you, where they deal with fundamental algorithms, very applicable, open source, like many of the libraries, especially the top 10 Python libraries for data scientists out there, right? And it can compete with C++ as well, and it's very, very simple to use on what we know. So let's try to see what we could get here and see what scipy entails. So ladies and gentlemen, we understand about the installation can install scipy through pip arcana, which is very simple and easy to do. And they could get all the stuff that's there. You can actually try to look at this stuff below, and you could go to scipy.org for more information below if you actually want to try and dig more into detail with this packaging. So we have here some documentation here on how scipy basically works. Developer guides, reference guides, user guides. You can definitely look at this on your own, but I want to try and deal with the getting started and see how this whole thing basically works. So we have a good user guide on how scipy works, which we know about special functions, integration, Calc 1, Calc 2, Calc 3, all that stuff. Optimization, interpolation, Fourier transform, signal processing, linear algebra, sparse eigenvalue problems, sparse graph routines, data structures and algorithms, basic statistics, multi-dimensional image processing, and then you have file I/O. So we go down the introduction, how it works. They have the mathematical algorithms to actually import with the extension that you see here, and they have the first time scipy user that basically deals with these functions. Cluster represents clustering algorithms. Constants deal with physical and mathematical constants. FFT pack represents a fast Fourier transform routines. Integration is the integration of ordinary differential equation solvers. Interpolation is the interpolation moving splines. I/O represents input and output. Lin-alg is linear algebra, and the image and dimensional image processing. ODR or diagonal distance regression, optimization, root finding routines, signal processing, sparse matrices and associated routines, spatial data structures and algorithms, special functions and statistics, stats, right? And then you could import which type of packages that you could try to find to install, and they have the documentations here that they will show as an example here. So we go down to special functions, right? I have a special functions is basically when you're doing differential equations that you see here. If you have done engineering math like I have years ago, or if you've done any advanced mathematics where you're doing a bunch of ODE transforms, PDE transforms, this may be the one for you. Or if you have a mathematics degree, in any case, right? If you have an engineering or mathematics degree, or even a physics degree, you definitely would fully understand what I'm talking about. But for those that actually just getting started when it comes with data science, and you don't have that much thorough STEM background, you may have a thorough hard time understanding this, which is why I want to try and make this as elementary as possible for you, to make sure that you be able to actually fully understand what really goes on. So this is how it basically works up here. The special functions basically deal with some integration functions that you see up there. Drumhead heights, all that other stuff, plotting figures, getting 3D motions up in there that you've shown that you can basically see. And they talk about Python bindings, right? So they offer that as well, where they have documentation, so you can definitely look that up below as well. And then you got the Python function overhead, which will definitely develop ranges, releasing basically the GIL. Alright, one second, I'm trying to see what it basically stands for. GIL, they basically release it, and they have basically a differential function where they have a change in gradient, So you got the Dirac Delta, the Dirac Prans, and then you can try to look that up on Google if you're having a little bit of trouble here. And you got Henkel 1. All this craziness, and you see some of these functions that aren't in special, scipy special integration, right? Same thing here. We got an integrate package that you see certain numbers. You integrate quad, double quad, triple quad, fixed quad, quadrature when it comes to the Gaussian formulas, as well as Romberg integration. Trapezoidal rules to integrate cumulative trapezoidal rules to deal with computing integrals, Simpson and Rom. ODE integrals when deal with ordinary differential equations, and ODE basically means integrating over ordinary differential equation, which deals with Vode and Z-Vode routines. So quad, they have this stuff that's there that deals with like a simple integration that they will actually discuss there, and you see the code that's down there below. You can definitely look that up as well under the user guides with the documentation, and you can definitely do like some complex integrals that you will see up there when it comes to complex analysis with Python as well. When it comes crazy, you can easily try to do that yourself also and knock this out. So they have a bunch of integral forms, exponential forms, the whole 9 yards. Basically knock some of the stuff out that you see here, and they have all the stuff that you see down below. All these outputs, multiple integration when it comes to general multiple integration, double quad, triple quad, n quad. Double quad basically means like a double integral. Triple quad basically like a triple integral, right? N quad is n integrals, how many times it needs to be integrated. That's basically what it means, right? So non-constant limits, this is your double integral here, and they have the definition here, and you got your double quad formula, and you type down the equation down below, and you type this area here that you would develop, which basically would be your double quad formula as well, in order to get the area within the, how do I say this, for your square, right? Or basically your trapezoid, or any basically four-sided figure that you would see here. I forgot what the word is, right? So n-fold basically requires n-quad, basically deals with nd, right? And integration bounds deal with like iterable objects, and could be a list of constant bounds or a list of functions. For non-constant integration bounds, which you would see here, and this is how it will be calculated in Python below, right? And I know a lot of math nerds actually going to be feeling what I'm feeling, because we know this is the Nerd Chronicles up in here. So we are having fun with this, right? So this evaluation here can be evaluated by means of this function right there. Gaussian quadrature, right? Few functions that also provide in order to perform simple Gaussian quadrature over a fixed integral, and they got the fixed quad, Romberg integration using samples, right? They have the code that's down there below, which corresponds to this integral here. We actually try to solve what x is, right? And this is how they would set it up in code, basically. And you integrate the second function, you get this stuff knocked down, and you do the order of the polynomial, dealing with a bunch of fast integration, the whole 9 yards, right? Basically have that knocked down, right? And you compile these links with fast integration with callback functions using double F, which you would see here below, and it has to be linked with a math library, right? Whether it's Linux, Mac OS, Windows, however it may be, right? And you use that shared library that you get from those areas, even if it's through SQL. You load that into Python, integrate it below, and that's how you're able to knock this stuff out, right? ODEs, right? Basically engineering math. Integration is a set of ODEs given initial conditions is another useful example, which it would solve IVP. Initial value problem, basically what it stands for, that's what it solves, what they have for scipy. So you basically integrating the first order vector differential equation, ODE. Given the initial conditions, y naught, y is to 0, where y is a length n vector and f is a mapping from one map to the other map, Rn to Rn, right? It's like one map to another, basically. So your higher order ODE can always be reduced to a differential equation of this type by introducing immediate derivatives into the y vector. And you can see all the calculations that you have below. And I know I'm going a little bit too fast for, the business nerds out there that aren't really fully advanced when it comes to this type of calculus. I know some that use like data analysis and all that other stuff, or business analytics, and they may not be that used to this whole deals. I may not know, I'm not fully sure, but those dealing with finance majors, those dealing with marketing majors, those dealing with any other business majors, wherever it may be, or any other courses that aren't related to the advanced STEM fields, you're gonna be off track by what I'm about to explain literally moving forward here, right? So you see integration here. You see all the stuff that basically comes down, and you got the Jacobian matrix that you see, blah, 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 and you see the matrices that you see there. All of this sets down. You'll be able to actually try to look at it below on your own. The site's right there for you to actually look for it. Optimization, right? They got so much content when it comes to optimizing functions, optimizing equations. And you see all these functions that you see up here. Interpolation, right? You're dealing with lens space. You're basically trying to interpolate graphs using the pi plots to see what goes on. And you basically would try to interpolate, the graphs and see how it basically works. Manipulations, basically for 1D, cubic spline interpolations, however it may be, right? So you basically try to figure out what the points are and see how these things work. Multivariates, they have those that's there. You got the original, nearest, basically like some data manipulation when it comes to images, right? And then you could definitely try and look more of this below. Fourier transforms, right? I'm sorry I'm going a little bit too fast because I want to try and keep it basic so that you'll be able to actually try to dig below. 1D Fourier transforms, this is your classic Fourier transforms that you see here. And again, another form of engineering math, right? Not the code below. Basically see that you're dealing with like a summation of 0 to the endpoint of x of n, basically at the function, right? You basically knock that down point based on like what the graph's behavior is, on how the Fourier transform basically works, and you see all the imaging literally below. Cosine transforms, sine transforms, same stuff. You can look at this in more detail below on your own. Signal processing, right? You're dealing with some filtering functions when it comes with B-splines, right? Basically knock some of this stuff out with manipulation and proofs, okay? All these images that you basically show when it comes with deep learning, AI, natural learning processing, doing the outputs, the whole ordeal, filtering, the whole 9 yards, dealing with convolution, dealing with a bunch of mathematical equations, literally the whole 9 yards where you're able to actually manipulate the images as you see forth, which could be another way to actually manipulate this stuff when it comes to deep learning. If you want to try and go outside TensorFlow, if you want to try and go outside Keras, and filtering the whole 9 yards, and they got this little D trend here. Linear algebra, right? So we got linear algebra, not modern algebra. We got like some linear algebra problems that you could definitely see when it comes with matrices, right? Finding inverses, the whole 9 yards. Solving linear systems, finding determinants, right? Dot products, computing norms, max, min, literally the whole 9 yards. Least squares problems, that whole ordeal. Getting all the data fitting that you see up there when it comes to matrices, eigenvectors, eigenvalues, the whole 9 yards, singular value decomposition, linear unit decomposition, LU decomposition, whatever variables they have up there, QR decomposition, then left arrays, Chokshi decomposition as well. They got all these codes that you basically try to deal with that you'll be able to try to manipulate on your own, that you'll be able to try to dig. Whether it's like the SOHCAHTOA, right? Trig, arbitrary functions, the whole 9 yards, they're all there. Sparse eigenvalue problems, right? They got all the stuff that's there when you deal with RPack, which is a Fortran package that provides routines for quickly finding a few eigenvalues such eigenvectors of large sparse matrices, right? In order for these solutions to be found, it requires left median multiplication only by the matrix in question, which is performed through a reverse communication interface, which RPack is basically needed, right? And that's how RPack is basically used for. We got the functionality that's produced in that. They have 2 high-level interfaces, sparse, analog IX, and spicy sparse, analog IX, providing interface to find the eigenvalues and values of real complex non-symmetric square matrix, while Aegis provides interfaces for real symmetric or complex Hermitian matrices. And I don't want to try to take too long digging with all these things below. You can definitely try and look at this stuff on your own to figure it out. Sparse graph routines, basically deal with like a manipulation when it comes to wording. Basically dealing with word ladders, where you actually basically manipulate certain paths between words, switching things one letter at a time, right? This here, boom, 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 boom. Get your word list out, get your stuff done below, important numping involved, hammer the distance, get everything down, and that's how you're able to see the manipulation go down below. Spatial data structures, right? Scipy spatial can compute triangulations, four-line diagrams, and convex holes of a set of points by leveraging the Q-hole library, which would contain KD tree implementations for nearest neighbor point queries and utilities for distance computation and various metrics. You see the one-line triangulations as an example, which deals with the subdivision of a set of points into a non-overlapping set of triangles so that no point is inside the circumference of any triangle. And they have triangles that tend to avoid triangles, small angles, which we will see here below, right? Co-plane of points, same thing. Convex holes, same thing. Diagrams, you see them same here. And again, you definitely look at this up on scipy.org with the full set of code below. Statistics, right? And you already know how statistics works when you do with random variables, continuous and discrete, all right? You got all these distributions you see here when it comes with help. Manipulating shapes, freezing distributions, broadcasting fitting distributions. All the stuff that you see here, Quasi-Monte Carlo. All this code that you see literally below. Okay? Up on the site, you definitely look at them yourself. And you see how all this stuff basically works with cumulative frequency. Deceptive the statistics, literally the whole 9 yards. Right? T distribution, multivariate estimations, right? Linear scales, right? Regression, however it may be, correlation, however it is done, 2D, 3D, ND, whatever it is, discrepancy calculations, the whole 9 yards is there. Go to scipy.org. Multi-dimensional image processing. We do image processing analysis can be seen on 2D arrays of values. Basically be used for AI, natural language processing, deep learning, however it may be, which you can share about all these functions that you show below. Filtering, interpolating, morphology, distance transforms, segmentation and labeling. You got all these manipulative words you try to use within modes here. You definitely look at them your own below and actually try to dig more of these things and how these functions and derivatives work, right? And I could actually try to scroll down there to give like a quick reference here to see how the code literally gets down. And again, you can look at this up below. They have all these samples that you can definitely print out as well when it comes with interpolation and when it comes with manipulation as well. Distance transforms, the whole 9-yard object measurements, extending the images that you see below and all the references that you see down here. Then you can actually try to dig a little bit deeper, right? It's all up in scipy.org. And last but not least, file.io. You got your MATLAB files here. We can load a MATLAB file if you choose. You guys still use MATLAB today. Save MATLAB files into a MATLAB style file that you have here. And you list variables that are down there, right? Where you basically do with like a scipy input output, right? When you do with tag competing, and can use that with MATLAB file, getting the input and the output, right? And this is how they will actually have them shape up here. MATLAB structures, right? MATLAB structs, they're a little bit like Python dicts, D-I-C-T-S, right? Except the field names has to be the strings below, right? And you can scroll all this down, see how MATLAB works, cell arrays, how they work, and boom, there you have it, ladies and gentlemen. And the scipy API, they have all these references that you definitely do, right? Signal processing, single matrices, the whole ordeals, clustering, doing all this stuff that you see there. That you have all the reference function, you have all these definitions below. You can definitely look them on the references to the scipy.org. Happy computing. Chris and Paul from the Nerd Chronicles signing out. Deuces, deuces, deuces. Good night.